Welcome back to Bits and Pieces, lecture number 1, Bits and Bytes. So before the break we took a look on how we could work with binary, octals, hexadecimal, how number bases work, how we can translate between them and so on. Well, we didn't work anything with the code or anything, so that's exactly what we're going to do now. Now we're going to head over to Dr. Java here and type some code. But before we can do that, I'm just going to write a simple program here, public class byte test. So we're going to work a bit with bytes, like that. And then, public static void main. Okay, there you go. So what do I want to do? Well, we were talking a bit about binary, and we also mentioned bits. 1 digit when it comes to binary is a bit. But what is a byte? We worked with bytes before without actually taking too deep of a look into what they are. Well, they are basically integers of a specific size. How big are they? Well, 1 byte obviously, but how big is that? Well, 1 byte is 8 bits. So that's how everything works in the end. We have bytes, and each of them are 8 different bits. So if we want to type that in binary, we can do so. If we start with 0b here, we can type it. As you see, it's adding numbers into a code, but when I do 0b, it's removed that. And the reason why that is the case is probably because this 0b thing that you can do so to type in binary is fairly new. It's in Java 7, so if you're using something before Java 7, then you can't use 0b here to type in binary. But I'm in Java 7, so it's totally fine here. And what I want to do now is 0b, and that's just defining we want to type in binary. And then what we want to do is add the different bits here. So 8 bits is 1 byte, so I'm going to do 1, 2, 3, 4, 5, 6, and then a 1, and then a 0, like that. Okay, so there you go. 8 different bits is symbolizing a byte there. So that's we can't store more than 8 bits in a byte. That's not possible. But now if we store it like that, we can totally print that out. So system.out.println, and then we just used the byte there. So what should this be? Well, we can just take a look. How do we do it when we calculate the go from 1 base to base 10. Well, remember we take how much we have on each position and multiply that with the multiple at that specific location. So this position is worth 1, but we have 0 there. This is worth 2, this is worth 4, 8, 16, 32, 64, and that one is special, more to that later. So what we have here is basically 2. So now if I run the code, it should print out 2. I need to save it, like that. There you go, and then it's just a matter of running it like that. So there you go, the result there, as you can see in the bottom there, you can see 2. Okay, but what if we want actually to print it out as 10? We can totally do so. We can just do integer dot to binary string like that. Okay, not 2 there, we want to be there like that. And then it's just a matter of running it. There you go. So we get 10, just like we typed here. So what we have here is not that the byte itself here is going to store this 10 here for us. We're still going to store 2. Or if you want to be very precise, what's happening is actually that we always store it like this. We store it as 0, 0, 0, 0, 0, 0, 1, 0, which is what represents 2. So even if we would have written 2 over here, like so, it would still store it as that, because in the end, like I said, the computer stores everything in binary, and therefore this is the exact same thing. I just type it using a 2 instead of using the binary form, but it's still going to save it as binary, and we can still convert that to binary there. But if I just use the number straight away, it's going to print that out as 2. Why? Well, it would be annoying for us to work with binary all the time, so therefore when we print out a byte, it's going to print that out as a decimal, so it's going to convert that. But in the end, what is being stored here, so this code is very simple. We store 2 in a variable and then we print it out. But what's actually happening behind the scenes, which you don't have to care about, but what is happening is that it's actually stored that as 0, 0, 0, 0, 0, 0, 1, 0. So basically 10, like that. In the end, but we will see it as this. So like I said, it doesn't really matter how if we want to add it as binary there or in decimal or anything else. So we can just do something like this, for instance. For byte I equals 0b0110, for instance, and then we loop through as long as that is less than 0b1111. And there we go. So what is this? Well, it might be a bit tricky to see it right away, but what I've done is I've added 4 bits here. It's still going to be a byte, it's just that I haven't added all 8, so what that means is that these 4 are zeros in front of that, but I don't have to add that. So what we have, which number is this? Well, we can take a look. So this is worth 1, we don't have anything there. This is worth 2, we have something there. This is worth 4, and that's worth 8. So we basically have 2 plus 4. That's 6. So we start at 6 here with I there, and then we can take a look on what this is. What is this? Well, we have 1 plus 2 plus 4 plus 8. That's 15. So we loop as long as that is less than 15. So it should loop all the way to 14, like so. And then we can just print that out, and what we will see is that it will go from 6 all the way to 14, like that. And that's just because, well, it doesn't really matter if we type it here as binary or not. It's not that we give it a different value, it's still just going to store the value in the byte there, and we can store up to 8 bits, but it's nothing special. We don't store any special value, we just define it differently here. And we can just take a look on that as well by using our little friend here as, again, integer dot to binary string, like that. And now we'll get all the binary, numbers from that one just below that one, basically from 6 to 14. And then if we move up here, and then we have it as this, and just like we had before, it's just printing out with binary. And we, of course, we doesn't have to do that. We can, of course, use other numbers here. So I'm just going to go from 0 to just below 8 there, and what that is going to give us is the 8 first ones, and those are the exact one we saw before the break when we actually talked about binary itself. So here we go: 0, 1, 10, 11, and then 100, 101, 110, and finally 111, like that. So those are the 8 first binary numbers if we start at 0, and we saw those before the break, like that. So like we can see, it doesn't matter if we give it as binary or in base 10. If we just add the numbers normally, it assumes that it's base 10, and when we want to print it out, it's going to print it out as base 10, but in the end it's still being saved as binary. That's how computers works, they save it in binary. Okay, so another example. What if we work with a short? What is a short? Well, a short is also an integer, right? And I've said it's a bit bigger. How much bigger? Well, it's 8 bits more. So a short can store 16 bits, which is basically 2 bytes. So when we store a short, we need to get 2 bytes from the computer to store it at, and well, the computer obviously does that for us, but in the end we're using 2 bytes, which gives us a total of 16 bits to work with. So what we can do is just 0b0 10 10 10 111 0 1 0 1 1, like that. So this is 14 bits long. So obviously we could add 2 more bits, so it would be the same to just add 0 0 there at the start, but I'm just going to leave it there. You don't have to fill all that up, but there you go, 14 bits, quite a long sequence there. And what if we want to do things with these numbers? Well, we can just add them together. Like I said, it's nothing special by by writing it this way. It's just that if we write it in binary, it's going to treat it like that. Otherwise, if we wrote this part here, basically what would happen would be that it would be 10,011, but now it's obviously not. Now, what is it then? Well, we can take a look. So we have a 1 there. That's the 2. We don't have a 4, we don't have a 8, but we do have a 16. So this is basically 16 plus 2, that's 18, plus 1, that's 19. So this is 19. But it works the same as just taking the number here, whatever that is, it's fairly big, and add that to 19, and then we will get that as a result. It's obviously going to be stored as binary in the computer, but when we have it, well, when we access the short here, the S there, we're going to get the value as if it would be a base 10, a decimal number, because it's going to convert that for us, like that. So now if I print it out, we're going to get, I think we're going to get 11,006, if I'm not mistaken. Yeah, there you go. So we get the result 11,006, and it just added this number here, and then added 19 to that. So what we have here is a short, and that goes from negative 32,000 to positive 32,000, if I'm not mistaken. There you go. So we can just add it like that, and if we want to, we can get it in binary as well, and we just do integer dot to binary string, and then we go with the S there, like so. Okay, and then it's just a matter of running that, and we get this result here. So 1 0 1 0 1 0 1 1 1. Yeah, and you can read yourself like that, and that's obviously the result if we add these two together. And it's fairly simple to see if we want to add them together. Okay, how do we add things together really when it comes to binary? Well, it works exactly the same. We have a 1, and we add a 1. Okay, what's that? 1 plus 1. Well, it would be 2 if we use base 10, but it's not. Well, we're obviously in binary, so therefore 1 plus 1 equals 10. And what does that mean? Well, that means that the result here, we can add the result here manually. And let's hide that so we don't cheat. It was there as well, sorry. Then we get a 0 there to the very right. But we have a 1 left to be added together with that one and that one. And therefore we get a 1 there, but we still have a 1 left to move over to that position, like so. So now we've added those two together. And well, actually, sorry, I can't select it properly. There you go. The 11 there and the 11 there is going to be 110 together. And then what we want to do is we want to add that 0 together with that 1, like so. So that's also 1. Then that 0 together with that 1, that's also 1. And then we want to add, well, basically this, well, we reach the end here, so we just have a ton of zeros here in the front. So what we can do is just take this part here and copy it in there, because we just add it together with zeros, and therefore we get this result. So as you can see, it's fairly simple to just add them together. You just have to remember that when we add a 1 and a 1 together, we get 10. We don't get 2. 2 doesn't exist in base 2, just because we just have two different numbers. We have 0 and 1, and if we check the result, it should be the same thing, and yes, it is. And if you want to make sure that it is, we can just paste them below each other like that, and there we go. So obviously you don't have to do the adding yourself in many cases. Well, yes, because we're coders, right? We can just tell the computer to do that for us, which we just did. It was just adding them together like so, and then we printed out the result as binary strings like that. So that's pretty much it. But here is some weird things. Okay, so to make this easier, I'm going to copy the result here and put that in a short directly. We can just put it here directly, so we can take an easier look there. Like so. So this is the result there, and then we print it out. Obviously we have the same result still. However, I'm going to remove some bits here. I'm just going to have 8 bits. So we have 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay? And I'm going to remove the rest here. So now we obviously get a different result, right? If we run it now, we obviously get the same thing there. But if we remove integer.toBinary string and just print it all out, we can see what this is going to be. I believe it's going to be 254, and there you go, 254. Right? So why do I do this? Well, let's take a look on this part. This is where it gets weird. System.out.println, and we convert it to a byte and then print it out. Okay, what do we get? -2. That's a bit odd, isn't it? So what we have here is a 254. That's obviously, well, lower than 256, and that's how many values we can store in a byte, but it's still going to be printed out as -2. But if you think about it, 254 is not within the range of a byte. It's smaller than the amount of things we can store, because 2 to the power of 8 equals 256. So we can store 256 values, but it doesn't range from like 0 to 255 or anything. It ranges from -128 to a positive of 127. Otherwise, we wouldn't be able to have negative numbers. So we wouldn't be able to store like int a equals -2. That wouldn't work if we just work with positive numbers. So you know, why not? So if we didn't do it properly, like think about, all right, we just work with positive numbers, that's fine. You know, then we wouldn't be able to have negative numbers, but we obviously have to store that somehow in here. So how can we do that? Well, like I said, the first one here is a bit special, but before we take a look on that, we'll take a look on the following. So if I have another short, S2 here, and I give it a value of, I don't know, 1, 2, 3, 4, 5, like that. So that's 8 different bits there. And if we count what this is, it's fairly simple. We have 0, we have 1, we have 0 there. So that's basically 2 plus 4 there, and therefore we get 6. We've seen 6 before there. And now if we print that out, S2, and we print that out as a byte as well, byte S2. So we'll ignore these ones for just a second. We'll go back to them in very soon. Okay, so now we get 6 and 6. So both of them print out 6. So there it works, and the reason why it works is the following. When we take a byte here, what we do is that we get what's called the least significant bits. With least significant bits, we take the bits to the furthest to the right here, because they are least significant, and that means that they are, like, their positions are worth the least. So we have the position that's worth 1, 2, 4, 8, you know, but we can only store 8 bits. So if we would have bits up here, it's totally fine for a short, right? Yeah, it is. So if I added like a 1 there, then that would be a part of the short, but when we would grab the 8 least significant bits for the byte, we would lose that information. So if we run it here, like that, we get 1030, and we get 6 there. So now we obviously get a difference, because we can just get the part here that we want. But as long as we only have information in the 8 lowest bits, then it's going to work fairly well, like that, 6 and 6. So that's not the problem that we have up here. So as you can see, when we convert it to bytes, that conversion is not causing any troubles, as long as we don't have any information further up in the most significant bits, the 8 most significant bits. So what's the issue here? Well, like I've been discussing, it's all about how negative things work. So this first bit, like I said, it's special. Why is it special? Well, it's determining if everything is negative or not. So what you might expect is like, alright, if this is negative, then we just convert this back. But we got -2. Like that's just silly. Why would this be -2? Well, let's take a look on what all the different bits are worth. Okay, so I'm just going to type comments here, what they all are worth. So we have bit number 0. That's worth 2 to the power of 0. Then we have bit, or well, we can actually type out what that is. So 2 to the power of 0 equals 1. Then we have byte, bit, sorry, bit 1 equals that, 2 to the power of 1, so that's 2. And then we have bit 2, That's 2 to the power of 2, just because it's bit 2, we get 4. So it's worth 4 if we have a 1 there. Then we have bit 3, so that's 2 to the power of 3, and that's equals 8. We have bit 4, that's 2 to the power of 4, equals 16. Then we have, so as you can see, I just double it here each time. That's how it works, because it's binary, base 2. Bit 5, that one is worth 2 to the power of 5, equals 32. Here we have bit 6, which is 2 to the power of 6, which is equals to 64. But now it gets special. Now we reach the special bit. So all of these are just, they make total sense, just binary there. So bit 7, what we would expect would it to be 2 to the power of 7, equals 128. But that's not the case. First of all, what I said was it's supposed to be determining if it's negative or not. So we could just say, alright, it's negative. But that's not correct. What we get then is wrong numbers. What it actually is, it's fairly smart. If you just think about it, it might seem very odd to start with, because why would this here be negative 2? But what we have is not that it's determining if it's negative or not, or in the end that's actually its effect, but that's not how it's defined. How it's defined is like the following. So we have 2 to the power of 7, but we have a negative version of that. So I'm just going to invert that like that. So therefore we get minus 128, like that. So everything here is positive apart from the highest bit there, the most significant bit, that's negative. Why is that so clever? Well, let's think about it. Let's take a look on the following example. So I have a byte here. I set the byte to 127. That's the highest possible thing that we can store in a byte. Print line, I want to print that byte out, and we will see that it's going to say 127, but that's not really interesting. So integer dot to binary string, like that. So if I print it all out to start with, then what we can see what that is represented as. Run, and as we can see, that's just a lot of ones. But how many ones? 1, 2, 3, 4, 5, 6, 7. So that's just 7 ones. That means that we have a 0 in the beginning. So 127 is obviously a 0 there. So we don't have that part. But all of the other ones we do have. 1, 1, 1, 1, 1. That's 5. There you go. So what we have is just all of these bits are being used. And that's obviously the biggest number that we can have. And the reason is because, well, we obviously want as many bits that we can to be 1, so we get as big as possible, but this bit here is obviously going to be negative, and therefore adding a bit there would make it smaller. But if we ignore what they represent for a second, if we just go back to our binary, what happens if we increase 1 here? I'm going to copy it over here. If we increase 1, what do? Well, we restart, 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 and increase it. So that's the next value. But what's the next value if we increase it beyond the maximum? Well, obviously if we increase it beyond the maximum, then we have to do something. We can't just get stuck. We can't just crash or anything. So what happens is that it loops back to the very start, which is negative 128. So if we go from negative 128 all the way to 127, the maximum number, from the minimum number to the maximum number, then we should probably restart at negative 128. And if we think about it, what is this number? Well, it's 128. We only have bit 7 here, and bit 7 is the negative version, and therefore we get 128. So automatically it's just going to bump back to this part here. So it's getting into 128 from 127, which is the thing that makes most sense. Like, where would we otherwise appear if we went beyond the maximum number? Well, then we go back to the lowest number. And then it's just a matter, well, we can take a look. So if I do b here and add 1 to it and then print it all out, print line, so I print b out here. Observe that I print it out normally, not as a binary string. Okay, and then I run it. like that. So what I get now is negative 128, yes, because we first had it like this, and then it was converted and turned like that. But what happens if we increase it by 1 now? Well, what happens is, you know, take a look. We should go from minus 128 to minus 127, right? And if we just think about the binary, what happens? Well, we add 1. Easy. What happens next? Well, like that, then like that, like that. And if we think about the result, what's happening now is actually we have minus 128 plus, what do we have? 100 there. So that means that we have plus 4, and that means that the answer in the end is going to be 126. Yes, because what's happening is the highest bit is not indicating if it's negative or not. That's just the effect of it, because it's negative itself. So if we have a bit there, it's going to result in minus 128. But the reason why we do it that way and not just say, alright, if the first bit is, well, 1, then everything goes negative, we just like inverse everything. Well, the reason why we don't do that is because now it makes much more sense when we count with it. Otherwise, if we would have a negative number and increase it by 1, then, well, the number would get decreased because everything would just be reversed. So we wouldn't be able to increase a number unless it actually was positive. Otherwise, we would have to decrease a negative number to increase it, and that wouldn't really make sense. So to start with, it might not make too much sense why this number here would be negative 2. But if you think about it further, it makes very much sense, and that's because this 1 here is representing minus 128 like that. So if we get all the way to negative 1, what's negative 1? Well, that's 1, 1, 1, 1, 1, and so on. So we have 8 ones like that, because then we have minus 128 plus all of these things, and as we saw before, 127 is all of these things. So we have 127 minus 128, that brings us to minus 1. What happens if we would take this number here and increase it by 1? Well, we can use our rule that, well, we reach the end, reset, 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 and oh right, we ran out of space. There's no room to actually add the 1 here, so therefore we just lose it, and boom, we're back at 0. So what we did was we just increased the binary from 0 all the way to up to 127. When we reached 27, we didn't have to bother about anything. We just continued with the counting, so we got to 1 and a lot of zeros, which is represented by negative 128 like that, and then we just continued until we reached minus 1, and then back to all the zeros there again. So now when we know that, when the highest bit is actually negative, we can go back and answer the question, why is this messed up here? Well, I haven't said anything that the 7th bit is always negative. What I've said is that the last bit is representing a negative thing. So what happens is that when we have a short has 16 bits. So what we actually have for the short is 1, 2, 3, 4, 5, 6, 7, 8 more zeros in there. So this one here is not representing negative 128. It's representing plus 128, just because it's not the last bit for a short. However, for a byte it is the last bit, because then we just grab both 8, and therefore the first one there is going to be represented differently. The first one is going to define that the byte is negative, and therefore we get minus 128 like so, and we finally add all of those together to get minus 2. So basically the difference we get is 256. Why do we get 256 in difference? Well, the byte version uses negative 128, and the short version uses plus 128, which gives us a 256 difference. Is that a 256 difference? It is, very much so. So 254 there, and we have negative 2 there, and that's the difference. So if we work with bits here, or even when we don't, when we convert things between, well, for instance, a short and a byte, we have to be very careful, because if we have a short here that is bigger in the number of bits that we use, if we have a 1 here, for instance, that one is going to be lost, obviously. But what we might not remember is that even if it's correct size, it's the correct size here, we still might get a difference just because this bit here is going to be the last one for a byte, but not for a short, and therefore it's going to interpret it differently, and therefore we get this negative side here. So what this means, well, what this is called is basically that we have a signed bit here. It's going to tell us if it's negative or not by having it like this. You can have things that is called unsigned. That means that if we want to have a negative version here, and that means that we would be able to store from 0 to 255 rather than what is it, minus 28 to 127. So we have the same amount of numbers. We still have 256 numbers to store, but they go from 0 to 255 rather than minus 28 to 127. So that's called unsigned. That means that we don't have a bit that defines that. That means that we can go higher in a positive range, but we can't get to negative at all. The problem, however, is that we can't do that in Java. You can't use unsigned integers in Java. That doesn't exist. Of course, you can define that yourself or use special classes and so on, but it's well, a normal primitive unsigned integer doesn't exist in Java. So the first one will always indicate if it's negative or not. But like we've seen here, it depends, of course, of the length of the integer, which one is the first one. Okay. What's next? Well, we can take a quick look at the integers and the longs, because we have byte, that's 8 bits. We have short, that's 2 bytes, which is 16 bits. Then we have an integer, the int here, that's 4 bytes, so that's 32 bits, which means that we can store pretty big numbers there. So we can store 2 shorts in one integer there, but we will have the same problems there. The first, well, the short one here, that one is going to indicate if the short is positive or not. That one is not indicating if an integer is positive or not. That's bit number, what is it, 31. And then we have the longs, which have 64 as well. So we can do it like this. I'm just going to add a comment here. So byte, that's 8 bits. Then we have short, that's 16 bits, or if we want 2 bytes, then we have the int, which is 32 bits, or if we want 4 bytes, and finally we have the long here, 64 bits, which is 8 bytes. So here you can see why we can store different sizes in different integers here. That's just because how many bits they have, how many bytes we need for them. Remember, 1 byte is 8 bits. Like that. Okay, so before we end, we should take a quick look on hexadecimal as well, because now we've only been talking about the binary here. So what I want to do is create a byte here. So obviously we don't use a different type. Hexadecimal still defines numbers, integers. So what I want to call this is, I don't know, my byte, there you go, equals, okay, so how do I write something in hexadecimal? Well, what I do here is 0x instead of 0b, like so. And 0x has been there for much longer than just Java 7, so it's just fine to do that. So 0x, 3, and d, like so. That's why it manages the colors here. Dr. Java hasn't updated, I guess. But there you go. So what does that mean? Well, that's the hexadecimal number 3d. Can we add more here? Not really. Why? Well, think about it. How big are these values? Well, they are 16 each. That means that a hexadecimal number, hexadecimal digit, is 4 bits. So therefore 4 bits and 4 bits, that's 8 bits together, and obviously we can't add another 4 bits here if we want to store it in a byte. But as we also can see, we have bigger alternatives if we so desire. So if we want to type this out, well, print this out, what do we do? Well, nothing special. Like I said, this is just how we represent it when we type it. We don't have to well, do that if we don't want to. It's still the same value. So I'm just going to print out that byte there, and then we will see the result, which I can't really remember what the result was. 56 maybe? No, 61. There you go. And we will take a closer look on that in well, right now actually. So why is it like that? what is this in binary, for instance? Well, let's redo it in binary. Okay. Byte, my byte, and now we're going to define the same thing. Okay, we start with 3, because, well, we have to start with something. So, what is 3 in binary? Well, that's, what is it? 0, 0, 1, and 1, obviously. So we have 2 plus 1, like so that's 3. Then, what we have to do next is, what's D in binary? That's a bit more tricky. What is D in hexadecimal to begin with? Well, A is 10, B is 11, C is 12, so D must be 13. And therefore we'll have to write 13 in binary. Okay. So how do we do that? Well, 8 plus 4, that's 12, plus 1, that's 13. So here we have 3 and there we have 13. Just put them together and there we have the binary version. Add 0b there to tell it that it's in binary, and now we should get 61 as well. Like that, 61 at the end. So as we can see, it's fairly simple to write it in hexadecimal instead of having to write 4 bytes here, 4 bits there all the time. And the reason we use hexadecimal in many cases is to make it more compact. Writing 64 bits in a sequence when we want to define a value might be quite long, but we might still want to define it with a base that is divisible by 2, so we can still easily see where we have the different bits, and therefore we can just do it like this. So as you saw, very easy conversion between hexadecimal and binary, just because, well, take the first 3 bits here. What are they? Well, that's 3, so add a 3. What are these things together? Well, that's 13, so take the 13th symbol, that's D, and there you go. So that's how we do it when we convert back and forth like that. But what we also can do to see that this works, we define this in binary here. Then we can do integer dot to hexadecimal string. I can't remember what this is called. It might be called hex string as well. Let's see. No, it wasn't. It should be hex string. There you go. Yeah, there you go. Which is going to give us 3D like that. As we can see here, it uses lowercase, so lowercase or uppercase doesn't really matter. We just need to use A, B, C, D, E, and F. If it's uppercase or lowercase, doesn't matter. It's not a difference when it comes to hexadecimal. So in some cases you use uppercase or you use lowercase. It doesn't matter at all. So as we can see, what we had here was 3D here. I converted that by converting the 3 first to 4 bits. These 4 bits. Don't forget the zeros, that might be important. So 0, 0, 11 like that, and then I converted the D there like that, and then we told Java to convert it back. So as you can see, Java can convert it without a problem, and we can also do octal string as well if we so desire. But that's pretty much it for today. We've seen how we work with binary, octals, hexadecimal, like different number bases, and seen a bit of how it works in code, how many bits we can store in different variables like so, but also this negative stuff. But let's take a bit of a summary, more organized summary right now. Okay, so first we started with octals. Here we go, we have 0, 0 all the way to 0, 7. Then, just because we just have 8 different symbols, we then jump to 10, 11, and so on, and continue there. Then, after that, we spoke about binary. Here we just have 2 different symbols, and therefore, well, we have to increase the amount of digits quite quickly. But we use the same rules there. If we went to the last symbol, then we just reset that and increase the other digit there. And finally, we have had hexadecimal. So we had 0, 0 there all the way to 13, but we didn't go the normal way. After 0, 9, we obviously had 0A, 0B, 0C, 0D, 0E, and 0F, just because we added 60 more symbols like that. So there we go. Then we spoke about how to convert things. So well, we did that before the hexadecimal part, but here we convert from octals to decimals, and to do so we just sum up what all the different digits are worth. As we can see, that's 2 there is worth 2 because it's a 2 times 8 to the power of 4. The reason is because we have 8 as the base and 4 that's the position, because the as we can see there to the right, we have 8 times a to the power of 0. So the first position is 0, and therefore we get 1 times 1 there, so that's worth 1, whereas the 2 is worth 2 times 4096. And if we add all of those digits together, the numbers times the position, how much that is worth, then what we get is 9001. And then we can do the opposite thing here, but we'll have to do it a bit different. So if we want to convert 541 in base 10 to base 8, what we do here is take 541 and divide it by the multiple of 8, yes, because we want it to be base 8. We have the 8 to the power of 3, because that one is the biggest one that is smaller than the 541 number, and what we get is a 1. But then what we have left is 29. The mod 541 mod 29, sorry, that's also wrong. 541 mod 512, sorry about that, equals 29, and then we use the 29 next time. We get a 0 there because 29 is smaller than 64, and then we have 29 divided by 8 to the power of 1, which is 8 then, but there we get 3, and then we get a remainder of 5, and that's the 5 that you see in the end. So when we convert 541 in base 10 to base 8, we get 1035, and it works a bit differently as we saw in the lecture. Just a short summary here. Like that. Then we work with the bytes. So what we have here is a byte with 8 digits, and each digit when we work with binary is called bits, so we have 8 bits in one byte, and we start with 0b there to tell it that this, what we're writing in, is binary. When we output it normally, we will get a 2 because we have 10 there in binary, but we can also ask it to print it out as a binary string, therefore it will print it out as 10 there. And then we can work with shorts here. They can store 16 bits or 2 bytes instead, and addition works normally like so. We can just add them together. We saw that during the lecture, and then we will print it out. We'll get 11,006 there. So obviously we get the base 10 value when we print it out, even though we have defined it as binary, so it doesn't matter what we define it as. In the end, it's always going to be stored as binary, and we will always get it as a base 10 number if we don't ask it for anything else. And then what we have here is the negative thingy there. So the first bit of an integer, because it's signed, means that that's going to make it negative, but as we saw, it didn't just invert it, it actually was worth minus 128, the first bit there. But since the short's first bit is not one of those 8s there, then we will have to, well, get a positive number because it's worth there. And finally, what we have was a hexadecimal here, so we could see that 0x3d is hexadecimal because we started with 0x, and the hexadecimal part is 3d there. And to convert that to binary, then what we did was to take the 3, which is 0011, and then we had the d there was 1101, yes, because d was the 13th number, and then we converted that into binary, and what we get is that thing there, 0b 00111101, and that's the same thing, and both of those are worth 61. And that's pretty much it. So don't forget the question and exercises document, questions for well, making sure that you have learned what's in the lecture, and exercises to practice that a bit more. Also some further explorations if we want to go a bit further. Answers to the questions and possible solutions to the exercises are in the end as well. But that's pretty much it. This has been Bits and Pieces, lecture number 1, Bits and Bytes. I've been WizWE, and remember, there are 10 kinds of people in the world. No one who probably realized that this was a joke in base 7 billion. Everyone's unique. Goodbye.